Hello, scholars. Welcome. Today, we talk about climate change. So you've heard me mention it in many lectures. At this point in our civilization, our human society, it seems like all roads lead to how do we solve climate change? It's the biggest pressing issue of our generation. And what we do now is going to reverberate through time, and it's going to echo our quality of life in 30 years. 2050 seems like it's the big number. We're shooting to have reduced greenhouse gas emissions to pre-industrial levels by 2050 in order to curb off an incredible amount of planetary warming that's going to be very deleterious and have impacts on biodiversity that range far and wide. Oceans will be part of that. They'll also be included in these adverse effects from the rapid onset of human-induced global climate change. So what we're talking about today is, what is climate change and how did we get here? How is it going to affect the oceans, and what can we do? So that's most of our overview. We'll talk about the carbon cycle. We'll discuss how human activities are causing climate change through the science. It's documented and proven. Earth's greenhouse effect impacts all life on Earth. It not only impacts us, it supports us. It's this beautiful thing that creates a stability of global temperatures that have allowed us to evolve and to sustain and to thrive into the societies that we have today. We'll look at how global climate change will cause many problems within oceans, and then how do we reduce and mitigate the effects from the current trends of increased global warming. Okay, so climate and weather. What the heck is the difference? Climate is what you expect, and weather is what you get. So climate is going to be the long-term averages, usually over a period of 30 or more years, for the daily weather conditions. Weather, on the other hand, if it's raining outside, you could say, right now it is 35 degrees and raining. That's the weather. Climate, you could say, we get an average of 3 inches of rainfall in the month of November. Climate is averages over periods of time. It is the trends. Weather is what we experience in real time. Averaged weather gives us climate. And when we're looking at climate, we're really looking at atmospheric conditions in relation to temperature, precipitation, and wind. We can understand a lot about systems by knowing the trends of temp, precip, and wind speed and direction. The climate system moves through all of the spheres of Earth, usually 4 spheres, but the hydrosphere, the biosphere, the geosphere, and the atmosphere. But in this book, for our intents and purposes, thinking about the oceans, we add in the cryosphere on top of that, which is looking at the world's ice caps, glaciers, and ice sheets, because they play a very significant role in global climate. So they get their own sphere here. I think you could easily wrap up the cryosphere into the hydrosphere as a part of it. But again, for our intentions in this course, in this book, we're going to look at it independently because, hey, it's that important. Our climate system is an exchange of energy and moisture between these 5 spheres. What happens in one sphere is going to affect other spheres. These spheres are interrelated components of the Earth system or of the climate system. Oceans are by far one of the largest contributors to the climate system because they cover 70% of the Earth. It's awesome. They're big, they're expansive, they're deep, they're powerful, and they are very, very important to Earth's global climate. Now let's talk about feedback loops for a second. A negative feedback goes like this. Brr, I'm cold. Let me put on a jacket. Okay, I'm not cold anymore. That was a response that went the opposite direction of the stimulus. Boy, it's hot. Let me take off my jacket. Now I'm cool again. Another negative feedback loop. A response in the opposite direction of the stimulus. Positive feedback loop, you can think about it like a snowball rolling downhill. The snowball rolls downhill. It gets bigger. It rolls faster. The snowball now rolls faster and it gets bigger. Because the snowball is bigger, it gets faster. Now the snowball is going faster, so it picks up more snow and it gets bigger. So the response is in the same direction as the stimulus. And when we take this into global climate change, we have these positive feedback loops where warming leads to more water vapor in the atmosphere. More water vapor in the atmosphere traps more heat. More heat leads to more evaporation, more water vapor in the atmosphere. More water vapor in the atmosphere leads to more heat. Both of these lead towards more heat. So the stimulus and the response are in the same direction. This is a positive feedback loop. And this is one of the problems with global climate change. One of the issues, I should say, is that we're heading in a direction where there doesn't seem to be any negative response to help to regulate what's happening from all of the increased greenhouse gases that are then creating a warmer Earth, which are melting polar ice caps, which change the chemistry of the oceans, which warm the oceans, which make them expand, which then leads to more evaporation, more water vapor. It's all in this similar direction. The stimulus and the response are in a positive direction. And the end result, if you're not confused yet already, the end result is that a little bit of warming leads to more warming, to more warming, to more warming. Herein lies one of the major issues of global climate change. So there's lots of feedback loops. In nature, predator-prey relationships are a feedback loop. In the climate system, we're looking at aerosols, air pollution, water vapor, ice reflectivity, ocean heat uptake. And what you get is carbon, and so the amount of atmospheric carbon and global temperature are highly attuned to each other because of these negative feedback systems, these negative feedback loops that keep a stability. Carbon is the flow of the carbon cycle. So carbon, we're made of carbon. I breathe in oxygen, I breathe out carbon dioxide. We're organic-based life forms. All life has carbon in it. Carbon is everywhere. Carbon cycles through the earth, through all these different reservoirs, through the biosphere, through you and I. It's locked in rocks way down underneath the surface of the earth. It's in hydrocarbons, petroleum, oil, natural gas. This is how we get to human influences of upsetting the balance of the carbon cycle, because carbon is everywhere. The ocean is like a biological pump. So the ocean can absorb carbon at its surface, and then through the process of phytoplankton using photosynthesis, sunlight, carbon, water to create oxygen and sugar, the remains, we've talked about this before, when phytoplankton get consumed and defecated from other animals, their remains will take carbon in their calcareous tests or shells and deposit it at the bottom of the ocean. This is one way to bring carbon out of the atmosphere and sequester it in the bottom of the ocean, and it acts like a pump. The ocean basically pumps carbon from the atmosphere all the way down to the bottom of its seafloor. We can see the biological pump here. CO2 is being uptaken by the ocean. It can also be released to the atmosphere. Respiration, photosynthesis, and decomposition buries these carbonate and organic carbon containing sources into sediments. Carbon's everywhere else in the entire Earth system, in the climate system. But it's really important that the oceans sequester it. And the oceans have done this for a long time, burying organic carbon deep in the ocean. And over time, this is what has turned into fossil fuels. Fossil fuels are hydrocarbons from the once living remains, the fossils of living organisms a long time ago that were buried in ocean sediments. So what's going on with carbon on Earth in our atmosphere? How do we know that humans are causing climate change? Don't climates change? Isn't this a natural thing? Well, yes. Climate change is a natural thing, and we'll get into it on how and why it is. But let's just look at it briefly, real quick, and then we'll get into it deeper. 800,000 years of carbon dioxide records. Where does this come from? Drilling into the ice in Antarctica and using air bubbles, oxygen isotopes, and the concentration of carbon isotopes in these ice cores to understand what global atmospheric carbon levels were through the past 800,000 years. And what do we see? We see a natural variability of carbon levels. To now, zoom, skyrocket. So in the last 800,000 years, we have never seen atmospheric carbon this high, ever, according to the records from sediment, or not sediment, but from ice cores. And warming doesn't happen this rapidly either. The steepness of this line here is much steeper than it's ever been in the past. So not only is there more carbon in the atmosphere, but we have more carbon entering the atmosphere more rapidly than we've ever seen through recent historical records. That graph I just showed you is looking at the paleoclimate data. This practice of paleoclimatology is how we study Earth's past climates. Paleo means ancient, or paleo means old. Climatology is the study of climates. So we're using things like tree rings, ice cores, bee pollen, glacial ice rings, deposits of coral, seafloor sediments. Here we can see an Antarctica ice core. Pretty cool. And so what these all are called proxy data. We're not actually measuring them. We've been measuring global carbon since 1880, and we have that record. It's a real-time record. We're actually measuring it. We have 800,000 years of atmospheric carbon through these other sources that are proxy indicators. They record the climate at that time that we're not measuring it, because you and I weren't around 800,000 years ago. Humans, Homo sapiens, weren't around. The most recent evidence of Homo sapiens is 300,000 years ago. Within the last 6 months, human skull, Homo sapiens skull, dated back to 300,000 years. So it shook up the understanding, because previous to that, it was 200,000. So these ice cores, I actually was reading some environmental news stories last night, and I came across an article that said an Antarctic mission to dig deeper than has ever been dug before is about to happen. So scientists and researchers at a research station in Antarctica are going to conduct a 4-year drilling mission to dig down deep enough so that they can look at the past 1.5 million years of historical record for climate, carbon, temperature. And that's awesome, because basically it's going to take this graph and it's essentially going to double it. So we can have a longer period of record to understand what's happened in Earth's recent history and compare it to what's happening today. Science is so cool. Okay, so who's to say what's happening right now isn't just natural? Could be natural. The sun gives off more heat at sometimes than others. You could say the solar energy that leaves the sun changes through time because of the nuclear fusion processes that are going on inside of the sun. Is burning hot. The sun is super hot. It's really real hot. I wouldn't want to go visit there. And so because solar energy changes, is it possible that the sun's amount of energy that is radiating to Earth has also changed, and that is what's causing our current trends of global warming? Possible, but not what the data show. And when it comes to this stuff, trusting the data, the thousands, if not millions, of scientists who are conducting scientific investigations to understand what's happening in our universe, on our Earth, with our climate. These are the experts. And what the scientists have shown us, what the science shows us, is that we can record the natural variability of solar irradiance, you can call it, the amount of radiation that's coming from the sun. And it does not trend with our current period of global warming. It did for a while. You could see from about 1880 to 1960, it looks on trend. But then the natural variability of the sun started to shift, where temperatures continued to rise. So, okay, the data show that the sun has a natural variability, but that's not causing our current trend of global warming. Got it. Well, how about these ideas of Milankovitch cycles? So this was a very, intelligent researcher who came out and he said, well, hold on, wait a second. There's an eccentricity to the Earth. So the Earth revolves around the sun on an elliptical orbit. That elliptical orbit wobbles a little bit. It shifts once every 100,000 years or so. Earth has an obliquity, which shifts about once every 41,000 years. And so that's saying the difference between 22 to 24.5 degrees changes. Right now we're at 23.5, but the oblique angle to the sun shifts about once every 41,000 years. Okay, stay with me. Precession. So Earth is kind of like a top spinning. And when a top slows down, it starts to wobble, and the angle starts to wobble. And so the angle relative to the sun actually shifts back to forth every 23,000 years. Okay, if all of that was like, what the heck are you talking about? We can break it down a little bit more simple. Because the Earth revolves around the sun and is tilted on an axis and spins, it causes a natural variability in those three factors: eccentricity, obliquity, and precession. Excuse me. Now, because of these, it induces periods of warming and periods of cooling naturally. We have recorded ice ages through the times. We know that the Great Lakes were carved by glaciers. Awesome. As recently as 18,000 years ago, there was an ice age. Awesome. Why do these ice ages happen? Snowball Earth. The whole Earth froze. Why? Because of the interaction of these Milankovitch cycles. Changes the orientation, the closeness of Earth to the sun, therefore causing natural ice ages. Gotcha. So ice ages, so cooler periods and warmer periods, natural part of Earth's history. Moving into a warmer period in 200 years, not so natural. Okay, what about volcanoes? There's evidence that simultaneously around the time that the dinosaurs vanished, there was also widespread volcanism happening. So did volcanoes kill the dinosaurs? Well, some researchers would argue yes. And there's also the giant impact crater in the Yucatan Peninsula in Mexico that shows there's a huge asteroid impact, sent a layer of iridium all over the Earth, blocked out the sun for who knows how many years had that happen. In recent years, we've seen, as recently as 1991, Mount Pinatubo, back to documented in 1815, Mount Tambora, Krakatoa, 1883, these large earth volcanoes, that is, eject so much particulate matter, pyroclastic material, into the atmosphere that it blocks out the sun, causes periods of cooling, changes Earth's climate system. Volcanoes are that powerful. They can have that effect. They also erupt CO2 into the atmosphere. So let's go big picture here for a second. The ocean is a biological pump that takes carbon out of the atmosphere and drops it into the bottom of the ocean. We know that the middle of the ocean is the mid-ocean ridge, and it spreads apart. When it meets a convergent boundary, those oceanic crust with seafloor sediments are subducted underneath the surface, causing a volcanic arc, island if it's in the ocean, continental if it's between oceanic and continental plate, and then volcanoes erupt. The eruption of those volcanoes have CO2. This is the movement of carbon through its various reservoirs. So cool. Periods of big volcanic eruptions, like the Deccan Traps, which we've seen covered 500,000 square kilometers in India, could cause increased global warming. But we're not seeing that many volcanoes happen in recent times. There isn't an extensive amount of volcanic activity, so we could rule this one out also. Okay, how about movement of Earth's plates? Tectonic boundaries can cause plates to move centimeters to tens of centimeters every single year. Now, when continents move, it upsets the dynamics of ocean currents. Ocean and atmosphere, the air-sea interface, intricately related. So when you have new oceans being formed or disappearing because of because of tectonic activity, heck yeah, it's going to change climate, but continents aren't moving on the order of 200 years. I mean, they are, but tens of centimeters to hundreds of centimeters. So a meter? Maybe we'll get one big movement along the San Andreas Fault and it'll be a jump of 30 meters. Got it. But that's not creating a new ocean. So because tectonic activity is a much longer pace, well, it's probably not causing our current accelerated climate change. Got it. So what we're doing right now is we're saying, what are all the natural causes of global climate change that Earth's history has experienced, and are they happening right now? So far, none of the natural causes could be happening, which will lead us to our next discussion. Are humans causing climate change? The scientific community says yes. I think this is great. So over 25 years ago, global warming came on the scene with the 50s, the 60s. I forget when it was first mentioned, but it was recognized a long time ago. Bill Nye in the 80s was pushing heavily. Hey, everybody, this is a big deal. He's still pushing heavily, saying the exact same things. More people are listening now, though. That's the thing. This is great. A study of peer-reviewed publications on climate change looked at 69,406 authors. And 4 of those rejected human-caused climate change because there's no convincing evidence against human-caused climate change. There's a multitude of data. So when you see a discussion of one scientist versus one scientist on the validity of global climate change, it's not really fair depiction of what's happening. If you had one scientist discussing with 99 scientists, that would be more fair. That would be a more accurate representation. Because the consensus among the scientific community is global climate change is real, and it's backed up in tens to hundreds, tens, thousands and thousands of scientific published journal articles. The science is there. It's not natural what's happening right now to our climate. So this group of scientists got together globally, forming the IPCC, the Intergovernmental Panel on Climate Change. 1990, they came out with a report, Climate Change is Real, Anthropomorphic means human-induced. Came back out with more reports, 2001 through 2018, looking at the trends and predicting rises in global average temperatures since the 90s. And today we still have this discussion. I don't think it's a discussion as much as, here's something. At one point, humans thought the Earth was the center of the universe. Ptolemy developed the Geocentric Model, and it was really good. It described a lot. Earth at the center, the universe is only as big as the solar system, and everything revolves around Earth. Well, not exactly it. Copernicus, 1600s, came out. He wasn't the first person with the idea, but he was the one who came out and proclaimed and said, the Earth is not the center of the universe. The universe, the sun is. And the sun is the center of the solar system. Galileo came out. He took a telescope that mariners used to look over oceans, pointed it to the sky, and said, wow, there's a lot out there. 1,600 years, people believe the wrong thing, when the truth is the sun is the center of the universe. And then the science came, and still people wanted to fight it. Galileo had to wait to publish his findings until he was on his deathbed for fear of retribution. And so now we're at this point where there's 70,000 articles indicating that human-induced climate change is a real thing. So public consensus is slowly catching up to the validity of the science that's already indicating what's happening. I think at some point in the next 5, 10, 20, 30 years, there's no more discussion. Is human-induced climate change happening? It's a new discussion. This is happening. We all know it to be true. And what are we going to do about it? We got to get there. The IPCC got the Nobel Peace Prize in 2007 with Al Gore for his movie An Inconvenient Truth. Check it out. Good things are happening. They're not the only organizations. There's also the National Research Council, looking at how we can reduce the risk of major disruptions to human and natural systems from global climate change. So there's major organizations out there who are doing really big things, and it's very important. Climate Science Special Report 2017. This came out and said there's no alternative explanation other than humans causing climate change. And we're going to get into how we're doing it here soon. But let's just set the stage. We know what natural causes of global climate change are, and they're not happening. There's no other explanation. All the scientists agree. Humans are causing global climate change. Whew. Okay. Glad we got that one out of the way, just so we can all agree. Now we have a framework for understanding how to move forward. Okay, let's go a little bit further back. Why is it called the greenhouse effect? Because Earth's atmosphere acts like a greenhouse. Heat transfers through radiation, convection, and conduction. Radiation is like your microwave. Put your food in the microwave, sends radiation waves through, and then boom, heats your food. Convection is like the water boiling in your pot. Conduction is touching the hot stove. Oh, getting burns from the contact. Shortwave radiation from the sun comes in, heats up the surface of the earth. The earth then emits long wave radiation. Light is just a wave. Heat is a light wave. Long wave radiation that then interacts with particles in the atmosphere, aerosols, water vapor, greenhouse gases that absorb that heat and re-radiate it back down. So just like a greenhouse where the sun can come in and then the glass walls keep the heat trapped inside, our atmosphere does the same thing. That's why it's called the greenhouse effect. This creates a heat budget. So there's addition and subtraction of heat from various sources. Addition, incoming solar radiation. Subtraction is going to be energy that is released as heat, conducted through the atmosphere, or evaporates and is absorbed through the clouds. This keeps Earth's temperature stable. Our global climate is stabilized because we have a heat budget that is regulated by the greenhouse effect. We call particles, here we go, particles in the atmosphere responsible for trapping and re-radiating heat back to the surface, greenhouse gases. Makes sense. There's the greenhouse effect, and it's supported by greenhouse gases. Water vapor is the most important. It accounts for 66 to 85% of the greenhouse effects. The water cycle, hugely important. My favorite cycle personally, and it's hugely important because it really helps to regulate global climate. Carbon dioxide is a natural part of the atmosphere. It moves. We breathe out carbon dioxide. Every breath we take. Carbon is not a bad thing. But our activities from the burning of fossil fuels has upset the balance of how much carbon dioxide goes into the atmosphere. And we can see from pre-industrial concentrations to now, it's tremendously higher than it was before. Data started to be collected from Mauna Loa in about 1955. I think I said 1880 earlier, but I was mistaken. 1955. Methane also is a greenhouse gas. It has a greater warming power. It's the second most abundant human-caused greenhouse gas from, throwing all of our waste into landfills. They're decomposing from cattle. It's got natural sources, and then also microbes. Methane is a big issue. So agriculture, consumption, and waste have led to increased methane. Fossil fuel burning has led to increased carbon dioxide. These are the big two. There's also nitrous oxide, CFCs, chlorofluorocarbons, which are banned now because they were causing a hole in the ozone layer, the protective layer that keeps harmful ultraviolet radiation from the sun from reaching Earth. There's a lot of human-generated greenhouse gases, but summary, carbon, methane, these are the big two. Okay, when we look at temperature, methane, and carbon dioxide, they track extremely well. Ice core data for the past 800,000 years indicates that increased period of carbon, increased warming. Decreased periods of carbon, decreased warming. Same with methane. There's feedback mechanisms that when temperature and carbon and methane get too high, there's negative feedbacks that drop them back down low. And so they oscillate around a median. We look at today's levels, skyrocket. skyrocket. So methane, carbon skyrocketing. Temperature hasn't skyrocketed, but it's following suit. And then here's the thing. We've never seen carbon and methane levels this high. So this is what's leading the prediction. If temperature tracks with methane and carbon are higher than they've ever been, then and temperature tracks with them, then it's logical to say that temperature is going to follow suit, and we're going to get a big increase in temperature as well. So David Keeling, 1958, Mauna Loa, started to measure atmospheric carbon. He was the first person, and that record has continued. His son, Ralph Keeling, now has taken it over. It's family business. I'm really interested to know if Ralph Keeling has a son, and he's going to be the next generation. Maybe this is just going to happen forever in the Keeling family. But what they noticed was there was a seasonal difference in carbon, most likely to do with phytoplankton blooms. When phytoplankton blooms, they're reproducing, they're pulling a lot of carbon out of the atmosphere and dropping atmospheric carbon dioxide levels. So there's a seasonal variation. The overall trend is increasing. We can see the natural variability of carbon still existing through the increased amounts of carbon. And it makes such logical sense to me. Pump carbon from deep within the earth and burn it, releasing it into the atmosphere, is going to increase the amount of carbon in the atmosphere. Carbon is a greenhouse gas. Put more greenhouse gases in the atmosphere, temperature of the surface temperature of the earth is going to warm. It makes so much sense. So we're looking at the future. What's going to happen? Business as usual. It's kind of funny. But that means, what if we just keep doing what we're doing and nothing else changes ever? We're cool. Excuse me. Well then, if business as usual happens, we're looking at up to 4 degrees warming. And that's average. Some places could be 2, some places could be 10. Really, it's going to be unequally distributed. Dry, hot areas, deserts are going to be affected, impacted probably the worst as far as increasing temperatures. If human emissions grow slowly, we could have a slow increase. If we reduce our emissions to year 2000 levels, we could level off where we are right now and minimize and have a 1 degree average increase. And that's ideal. We have the technology. Hey, let's do it. Stop burning fossil fuels, or start to implement policy and systems currently where it will help to influence our behaviors and our choices. So in 10 years, we're all supported to live a life that still suits us while decreasing our carbon footprint or the amount of carbon that you and I are individually burning into the earth. Other things to worry about. Other aerosols in the atmosphere. Things that we burn, things that particles in the atmosphere that will affect reflectivity and Earth's ability to trap heat. The albedo is the reflectance of the Earth. Ice has a really big albedo. Sun bounces off ice. The sun interacts with ice. It reflects back to the atmosphere, out into space. Shortwave radiation, and goes straight through the greenhouse gases. Melt the ice, now expose land. Sun's radiation is absorbed by land. The land then re-radiates it, contributes to greenhouse effect. So we've got to think about the cover of ice on Earth, the cryosphere. Again, it's very, very important. Not only are we predicting temperatures rising, but we're recording it. We've literally seen temperatures on the rise. This book was printed in 2018, so from The 10 warmest years on instrumental record occurred since 2005. 2018, 2019, 2020 also. So you could probably say the 13 warmest years. 2015 through 2017, this statistic's probably updated to say the last 5 years on record are the 5 hottest years ever recorded. Wow. If that's not something, I don't know what is. Sea surface temperatures are recorded. Basically, if we can measure it, it's getting hotter. And that's not some idea. That's not some prediction. That's not a hope. That's just looking at the data. I think you may even know 2019 and 2020, 2021 were horrible years for fire because it was so hot and it was so dry. We're in drought conditions here in the Central Valley. Average rainfall, snowfall, precipitation is below average. And 2021 had the most days over 100 degrees in Fresno on record. It was the hottest summer that we had ever seen in summer 2021. And it felt that way. Just living here, I could tell you without reading anything, it was hot. Over and over and over. So, okay, yeah, I'm experiencing it. You're experiencing it. It's not, we don't need the science. The science is there, but we could just anecdotally say, hey, things are getting hotter outside and it's shifting and it's changing. Heat waves. They're happening here. They're happening there. They're happening everywhere. It's a big thing. So what is going to change? Well, earlier hotter summers, seen it. More severe droughts, experiencing it. Bigger floods, reading about it. Worldwide retreat of mountain glaciers and ice fields, definitely happening. Water contamination, that's a big issue. Ecosystem changes and extinctions, happening. So predicted changes from global warming, these aren't predicted. These are happening. Should probably axe that and say changes from global warming that are happening right now. Increasing ocean temperatures. The oceans are getting hotter. When the oceans get hotter, they absorb more heat. They get bigger from thermal expansion, which leads to sea level rise. Hurricanes. More frequent, higher intensity. More Cat 4s, Cat 5s hurricanes are happening. We've seen devastating hurricanes in the last 15 years. Hurricane Katrina, one that we all know about, was one of the most costliest and deadliest hurricanes that we've seen. Wow, okay, happening. Deep water circulation. So thermohaline circulation is how water moves around the ocean on the surface in deep ocean currents, and it's very connected. When you have inputs of fresh water from melting ice caps, it changes the salinity of the ocean. When you have salinity differences, it's going to affect where you have upwelling and downwelling. This can upset the balance of the global conveyor belt that transports heat around the planet. So, changes in deep water circulation can have immense effects on the heating of lands from the distribution of heat of these deep currents. This is Arctic amplification, kind of what I just talked about. Losing Arctic sea ice enhances warming because of a decreased albedo. Less ice, less reflectivity, more land, more absorption. Upsets the balance. The age-old, sad polar bear. I don't think we could have a discussion on global climate change without an image of the polar bear. And what this is this exemplifies species that are being pushed out of their natural habitats because of global climate change. Polar bears need ice to eat. When the ice melts, they don't have a place to hunt for seals and gain their food. So, the ice melts, the polar bears die. And it's not just polar bears. It's a lot of species that are adapted 2, the environmental conditions of a certain ecosystem of a certain place, that when you change that baseline climatic condition, you remove viable habitat for that species. So polar bears are just a representative for a decrease in biodiversity from global climate change. The biggest ice sheet in the world covers Antarctica. It is melting, calving, where the ice sheet makes its way from land into the sea. 2017, a Delaware-sized iceberg broke off Antarctica. I don't even think we can fathom what that means, but chunks of ice as big as states on the East Coast are breaking off, and Antarctica is melting because it's getting hotter. That's not good for global temperature and for biodiversity and everything else that we're talking about, really. Ocean acidification, we've talked about this many times. The oceans absorb carbon. If there's a lot of carbon, the oceans will continue to absorb it because the ocean water is a great solvent. The more carbon is absorbed, the pH, or the relative abundance of hydroxide to hydrogen ions, changes. And so the ocean becomes more acidic, thereby affecting biodiversity and ocean life, especially adapted to the stability of the ocean environment. More CO2, warmer oceans. Warmer oceans, thermal expansion. Warmer atmosphere, more ice caps melting, ice sheets melting. More water in the ocean, higher sea level. This will affect all of the individuals that live in coastal areas who will be displaced and then become climate refugees. Not good. Models predict sea level rise of between 2 and 5 feet by 2100. 2 feet might not seem like a lot, but it's enough to flood entire coastal areas. 5 feet, pretty significant. Already, we've seen sea level rise of between 0.1 and 0.6 feet. So seas aren't currently substantially rising, but they are. And with increased warming, they will continue to do so. More things to worry about. This is going to change a lot of other features. Sea level rise will change the dissolved oxygen. It will change where we have marine dead zones. It'll change the wave dynamics of wind and wave heights. So the changes of a global climate increasing are pretty far-reaching. It's going to affect a lot. Migration of mangroves. Okay, so mangroves are trees that live in these hypersaline coastal waters, and they need a certain climate. Well, as it gets warmer, they're moving with the increased heat. So mangroves have been seen to have been migrating north. Changes productivity in the ocean. Decreased productivity from less upwelling. If we remember coastal upwelling and downwelling. It's led to a decline in phytoplankton biomass because phytoplankton need two things. Primary productivity. What does it need? Two things. Sunlight for photosynthesis and nutrients. Nutrients coming from upwelling of deep water sources, or you have the absence of a thermocline. But global climate change is increasing the presence of a thermocline, keeping the nutrients down away from the sunlight. So therein lies another factor affecting the oceans. Marine organisms are catching the brunt of these physical changes that are happening to their environments. Affect the environment, affect the organisms. It goes hand in hand. Okay, what do we do? What do we do? Well, we can talk about it like we're doing right now. It's really important that you and I come together and we have these discussions. It's awesome. The Paris Climate Agreement. It's a pretty big one where countries in this world have agreed to work together to reduce greenhouse gas emissions below 2005 levels by 2025. Huge. It's saying we as a nation agree that we commit to reducing our greenhouse gas emissions. This is really big. The number one way to ward off the problem of too many greenhouse gases in the atmosphere is to stop emitting them. It's not rocket science for this one. If greenhouse gases are the problem, let's not emit so many greenhouse gases. Other things that have come together, the Kyoto Protocol in 1997, the Copenhagen Accord in 2009, the Durban Platform. These are all big meetings. COP26, which just happened over fall 2021. Great. Another worldwide climate change conference where leaders are coming together to talk about the present issue at hand, to make commitments. Now we just need to move beyond commitments into implementation, into policy, into laws and regulations so that we truly can reduce our effects, our human-caused effects of global climate change. How do we do that? Renewable energy. Solar, wind, huge. How about for the oceans? Well, we talked about them. Wind turbines in the ocean, using ocean currents, wave currents, tidal energy. Awesome. Technological innovation, bright young scholars like yourself who are coming together saying, we need to solve this problem because it's a big deal. It's a big deal. It's a really big deal. So, utilizing new technologies, developing even newer technologies, developing technologies, is one way we can reduce greenhouse gases because we have a large human population and we have a society that is built with a dependence on energy and electricity. Our dependence does not have to be on fossil fuels. It is, but what do fossil fuels provide? Energy. So if we can flip our energy dependence from fossil fuels to alternative to green technologies, then we can stop using fossil fuels because guess what? They're causing global climate change and they're going to run out one day anyways. They're non-renewable resources. Okay, got it. Behavior, choices, choosing, buying an EV vehicle, putting solar on your roof, turning your lights out, using less electricity, making choices as an individual to decrease your carbon footprint or the amount of carbon that you as a single person emit into the atmosphere. When you do your carbon footprint calculator, you'll be surprised. It's surprising how much carbon I emit, how much carbon you emit as individuals. There's a lot of built-in carbon emissions that we don't even think about in our daily lives. So thinking about it and reducing it is one way that you and I can make a personal contribution. Big impacts are a series of small choices that you and I make as consumers and as individuals. You are important, just as important as I am and everyone else, in having a say and a voice into the world and how the world works that we live in. I truly believe that. Geoengineering, this one's kind of scary, but it's on the table. Cloud seeding, iron fertilization, carbon sequestration, just storing it and burying it in the ocean. These are ideas. They're innovative. My personal take is we should not upset the balance of the climate system to come up with solutions. But these solutions are on the table. Iron fertilization. Throw iron, which is a nutrient, into the ocean. Phytoplankton blooms. Phytoplankton pull carbon from the atmosphere and drop it at the bottom in marine sediments. Sounds good in theory. What about all the extra iron in the oceans? So, some tests have been done, but this is currently not allowed until further testing, analysis, and authorization has been permitted. Marine permaculture. So this is building kelp forests, which would create habitat, create buffers for seawater acidity, support greater ocean life. Okay. Sequestering excess carbon. Basically taking power plants, using the fossil fuels and burying them somewhere in the bottom of the ocean. Doesn't get to the root of the problem that we shouldn't be burning fossil fuels because it's causing excess carbon in our atmosphere. Doesn't solve the problem. It would be a band-aid fix. Solving the problem is moving our dependence away from fossil fuels and learning how to exist in a society that has low to zero emissions. What do we do next? What do you do next? Do we all just go home and bury our head under the pillow and cry for the rest of the day because it seems so sad, like there's nothing we can do? Well, maybe not the rest of the day, but a little while? Yes, because we should care about what's happening in this world, making decisions. My personal decision, I'm trying to make my entire house run on the solar that's on the roof. It's a 10-year goal. But I want to, here's the idea. We may have heard of going off the grid. I'm going off the grid. I'm buying some property out in this land, and there's going to be no one around, and I'm going to dig a well, and I'm going to be completely off the grid. That's great, but check this out. I like living in the city. I like my house. I like my neighbors. I like my community. I like my life. I don't want to do that. So this is my current idea. Can I go off the grid in my house where I live? I don't see why not. Get enough solar on the roof. Have enough electricity generating infrastructure, and then shift. I have an electric water heater that doesn't run on gas. I'm replacing the electric dryer that was in the house when I bought it by putting in 240 so I can put in an electric dryer. Removing all the gas and trying to create enough electricity so that my house is self-sustaining. It's off the grid. And hopefully it produces enough electricity that it can put energy back into the grid. What the heck? Why not? That's my own personal decision. It's my own personal choice, my impact. Teaching about this, talking about this, having discussions about this, and being open to, hey, people like you and myself, we can make a difference. So let's hold our head up high. Let's do what we can. Protect our world, our earth, our oceans, our environment, and ourselves in these decisions that we make. So that is oceanography. Everything, well, not everything, a lot of introductory concepts that cover the breadth of the ocean, how it functions, its properties, what's inside of it, how it works, how it interacts with other systems on the earth, and then bring it to today's big issue at hand, climate change, the effects of the ocean. If there's one thing that I can leave us all with, it echoes the words of Sylvia Earle. The fate of the oceans reflects our own fate. Because humans, the oceans, the environment, they all function together. And if there's an upset in the balance of one, there's an upset in the balance of them all. So as we upset the balance of our global climate, it affects our oceans. As we hurt and harm our oceans, it in turn will come back to us. If we can protect our oceans, sustain our climate, then what we're doing is preserving the quality of life for us as a species and also us as individuals who have a lot of potential for our own personal impacts during the time that we're alive on this earth. So you truly are the future. You are so important. Your decisions matter in what you do, and understanding how things work is the first step. So you're on a journey right now towards sustainability, towards understanding, towards contributing to a happier and a healthier world. And for that, I thank you. Thank you so much for taking my class. Thank you so much for all of your participation, thoughtfulness, and hard work. I really appreciate you and wish you all the best. Thank you.